Hi, in my previous video, I have already reversed the front part of the handle using the PETCF, and in my calculation, it should be as strong or stronger than the original part. And in this video, I'm going to reverse the back handlebar. The back handlebar extends longer than the front. It is more likely prone for breaking than the front handlebar. So after I made the reverse, I will print with the same materials, PETCF10 from Kexcelled, and I do a lifting test to see if it can really hold the weight of this EUC, which is 40 kilograms. We'll see if my calculation is correct. It's a cantilever beam about 14 centimeters long, and this is the fixed end. The designer spaced these two mounting holes apart to make it able to resist the bending moment when it's lifting up or being pushed down. Originally, this part is modeled by using loft command. You can see that it's slowly changed the shape as it goes along the length. These 4 points are not on the same plane, indication that they use loft command to create this. So when I reverse this, I'm going to use the same command that used for creating this part. Okay, the part has a reflector on both sides. I don't want to remove it, so I will use the spray to cover this up. I think I can make only 2 scans, front and the back, and then I have to merge them with just 2 scans, because if I make a 3rd scan, I need to stick it on the clay. But I think it's faster just to make 2 scans and merge them. If I raise it up a bit above the turntable, maybe I can get more than 95% of the scan. And the scanner that I'm going to use today is the Creality Sermoon S1. Okay, first I'm going to do global marker scanning. So with the laser, you can scan to the extreme bottom edge of the object. For the resolution, I'm gonna choose 0.2. Fill supply cloud in a batch process. Click on mesh processing. Alignment. Let's try automatic alignment. Maybe it can merge this. But it's just 2 scans. It can merge. You can see this is a low quality scan. It's in the extreme edge. Let's see if it will be removed when I do the mesh. We have 2.7 million triangle, so I will use 2.8 for the meshing. Click on apply. Okay. See now? The low quality mesh is automatically removed. You see this? It's all gone. And the scan quality is very good. So I can just make only 2 scans to reverse this part. I'm going to export this as the ASC format, align it in the Cloud Compare. This is in Cloud Compare. I'm going to change the color. I'm going to put this face on the XY plane. I have a 4K 32-inch monitor, So I can see in the micron levels. So if you have a smaller monitor, this can be difficult for you. Okay, now it's aligned. I move the bounding box to the origin. This center of the yellow box will be at the origin point. Next, I'm going to save this as the LAS files format. Okay, I want you to look at the mounting face here. After Miller, both sides of the model is aligned with the point cloud. This is because it was scanned with a high precision 3D scanner. So if you use a lower precision 3D scanner, when you mirror your part to the other side, it will not match. Okay, let's do stress analysis. PET. I'm going to fix the mounting holes here, and then I'm going to apply the force for 20 kilograms, which is 200 newtons. Run the simulation. Stress concentration on this area for 22 megapascal. We have a maximum stress inside of the hole. It's a bearing load. It's only 22 megapascal. Technical data sheet of the Kexcelled. When it's printed in the XZ axis like this, the maximum tensile strength is 113 megapascal. So it's strong enough for the 20 kilograms load. Let's try maximum load, 40 kilograms. Okay, it's still only 45 megapascal. So if I look here, it's plenty. This 45 megapascal is about half of the maximum tensile strength. So this part is safe for using. Okay, this will be the photograph from one of the users. He broke the rail handlebar. It's the same one in this simulation, and you can see that it's break along this line. So it's possible that he crashed. You can see the scuff mark here. The load is higher than 4 kilograms, and it breaks here in this 90-degree corners. So this will be the point that it breaks. Okay, let's take a look at the displacement. You can see that it moved only 2 millimeters at full load, 40 kilograms. So this is how it will move with the stress plot. So this will be the point of the failure. Okay, this is a Creality print. I'm going to drag and drop the files here. Okay, I changed the filament to PET CF. I'm going to face this one down here. And next I'm going to activate the support. And for the wall, I'm gonna need 3 walls and infill for 25%. Let's slice it. Okay, it requires supports here. So this is going to create a steps on the top layer, and it's not avoidable because I have to print on this orientation to get the maximum strength. Let's send this to the printer. Okay, this is Kexcelled PET CF. I'm drying it during the print. I put it in the Space Pi X4, and I'm drying it at 80 degrees Celsius. Humidity is 16%. This will be the first layer. So the nozzle is 290 and the build plate is 90. Support removal is very easy when the filament is dry. Just pull right out. So I highly recommend that when you print engineering plastic, you need to dry it. It will affect the strength and also the support removal. And it looks very nice. This will be the area where the support is. I think it's look really clean for the support area. This will be the bottom side. Curvature is perfect. I think it's stiffer than the original part. Okay, injection mold 156 gram, PET CF 88 grams. So lighter than the injection mold. Okay, this will be the original handle, injection mold. So it's hold to the frame, a metal frame with two M5 screws. So one in the back and one in the front. And this real handle also used for protecting the shock absorber during the impact. Okay, let me test lifting with the original handlebar. So the weight of the EUC is 40 kilograms. So one handle is 20. So when lifting, you cannot lift like this with two hands. But sometimes a user can hold it with one hand like this. So this handle is holding 40 kilograms. And the front handle 40 kilograms. So I'm going to test the 3D printed handle using both hand and one hand, not one hand, holding it with just one handle. Okay, let's switch the handle. Okay, let's check the fitting clearance. So fit, there's no gap here. That's why they have a notch here. And there's no gap here. So it's flush against the frame. Let's do the lifting test. Okay. Okay, next front handle, one hand. Okay, front handle is working. No handle. Okay, rear handle is working. So the calculation is correct. One handle can carry 40 kilograms of the load. PET CF10, if you print it correctly and do the calculation before you print, it can safely replace the stock injection mold ABS part for the structural component. And it's lighter, 80% lighter than the injection mold part. I think it's cheaper too. This one is only 92 grams, which is about $3 US. The cost of the filament and dimensional stability is good, better than the nylon. So I highly recommend it. You don't have to do a post-processing or painting. The finishing already look good. Thank you guys for watching. See you in the next video.